Hello everyone and welcome to our talk, Stream Processing but for Microservices, talk about Restate. In this talk today we want to show you a bit of the new project we're working on called Restate. It's in very early stages. It's currently available in a closed beta that you can get access to on that URL. We're planning to open source this in the coming months. But we'd like to show you where this is going and what you can expect. It's a pretty interesting system. I think there's nothing quite like it. There's lots of ways to think about it. Maybe the easiest way for this audience to think about it is it's kind of a way to build event-driven applications without really thinking about event-driven applications. All right. So just putting this on the map. Wait, is this? Oh, no, that's actually correct. Yeah, just putting this on the map. The spectrum of stream processing applications, as I've typically thought about them, is kind of not too far away from like the database applications, the more OLAP applications, the more OLTP style applications. And for streaming applications, you kind of find a similar spectrum. So a lot of work has been done to serve the more analytical use cases over the last years. Systems like Flink, Kafka, Materialize, all those being really built for those use cases and excelling at those use cases. And Restate is kind of the complementing piece in our mind to that. So coming from the Flink background, Restate is kind of built to do those things well that Flink never did well. You can kind of think it like that. So the more event-driven state machine type of applications, distributed actor applications, RPC-based microservices, and so on. And those are actually, in my opinion, pretty important, but pretty hard applications, right? Those are the applications that kind of drive a lot of the day-to-day online business, right? Like moving funds and inventory, redeeming vouchers, signing up users, and so on, managing incidents, like all those, all belong to kind of that category. And the state of tooling for that category is, I think, not great, really. In the general case, when you're developing these type of applications, you're actually a full-on distributed systems developer. So you've got to worry about everything as soon as you leave like the single process monolithic design. And with the cloud and all the different services you usually interact, that happens pretty quickly. So you're worrying about like distributed race conditions, dual writes, item potency that just might get very violated if you have a network partition and so on. It's lots of things that go wrong really quickly. And the impact of those things is maybe, it seems initially subtle, but it's actually pretty big. This is a blog post from right about a month ago that really looked into the state of like distributed bugs, and I think it's very interesting what they found. It's called Smashing the State Machine. I think that's actually a great title. It's really about like what goes wrong if you don't get your distributed state machines right. And you can do pretty impressive stuff, like you can withdraw more money than you have, you can redeem vouchers multiple times, you can bypass security measures and so on. So there's a case to be made to get it right, I would say. Restate is a tool that we're developing to help get this situation a little bit remedied, like making it easier to build these applications. The way we're describing Restate is saying it's a way to build resilient applications using distributed, durable, async await. That sounds a bit ominous. Like what does that even mean? And you might recognize async await from languages like Python, JavaScript, Rust, Kotlin, and so on. They're the programming language constructs and keywords for promises, futures, coroutines. Those are pretty powerful building blocks, right? I would say in every language where they came up, they kind of revolutionized the way people build concurrent applications in those languages. It's much different than like locks and chaining, futures, and I don't know, all the other hoops you have to usually jump through. Like it's really an easy way to write concurrent code that's actually very resilient. And Restate you can think of as a bit of our take is like trying to make this approach durable in a distributed manner, because if you actually manage to do that, you can express a lot of different distributed applications in an easy and in a very resilient manner. And the whole thing is actually powered by an event-driven stream processing style underlying infrastructure, but you don't really see much of it. So that's the idea of you writing event-driven applications without actually thinking about them. So where Restate sits is So before we actually show the code and go into the demo, just like a few high-level pieces about it that I think you need to understand to really get the demo. So Restate sits in your stack in a place that's not too different from Kafka. It's built for very different things than Kafka, but it still sits between services. It connects them in a pub sub or a message hub kind of way. It has a server component, which is the Restate runtime. It's a distributed, replicated system. It's actually built as a compact single binary in Rust. You can deploy it and just scale it. And then it has a client component, an SDK that you run in their service. Like not too different from the Kafka consumer or a JDBC driver. The closest thing to Restate, I don't think anything is really close, but maybe if you've used Amazon Event Hub or something like that before, it goes a little bit in that direction, and that's actually a push-based system that pushes events to services rather than being a message queue that you pull events from. But it does that in a very specific way. And when it pushes events to systems, so it actually makes an invocation to a system, it allows you in the context of that invocation to access a lot of pretty powerful primitives scoped to that specific invocation. Like you can actually anchor reliable RPC in that invocation, access durable execution primitives, durable timers, store data in the context of an invocation, and even access workflow primitives. It sounds very vague, but it will become a bit clearer in the demo in a second. The last thing I want to do before we jump in the demo is just highlight a little bit what the life cycle of an event processing step is in Restate versus Kafka, because I think that's kind of instrumental to understand everything. So just to recap how things work in Kafka, I guess most folks are familiar how things work with Kafka, but I just want to point out three things that we do quite different in Restate. And the first one is, I mentioned this before, so Kafka is a pull-based model. You have a consumer. The consumer connects to the broker and pulls events from there to process them. Maybe that's kind of a trivial conclusion, but it means the process has to actually be there to run a consumer and pull the data. The second one is you're getting an event. You're getting an event in isolation, which also may seem, yes, okay, of course, what's the deal? But if you actually build application, you rarely look at an event in isolation. You usually look at an event. You need a lot of contextual information about that event. If you're getting an event about a user, you often want to look up stuff about that user. And you do that manually, right? Maybe that feels natural, but I think that's important to remember. It's your responsibility to gather every contextual information about the event that you need from external databases. Maybe if you're in a KStreams style model, you have an embedded RocksDB where you gather that information from. But the process is actually a full state managing process, which makes it somewhat not trivial. No matter whether it's the backup of that state or the synchronization with an external data system, it's not a completely trivial task. And the third bit is recovery is absolutely your concern, or consistency and failover, right? You pull an event, at some point you commit the offset or acknowledge the event, and everything in between is up to you. So if you actually interact with other systems in the meantime, it's really for you to think, where do I actually put the acknowledgement? Do I put this first? Do I put this last? What gets duplicated? Are those idempotent? What does not get duplicated? Where do I want to write ahead and maybe pick it up later after recovery? It's all your personal sort of business to figure this out. Maximum flexibility, maximum complexity. Restate takes a bit of a different approach to those things. The first thing to probably point out is that the Restate broker is a bit more of a rich component. It's actually a log-centric system. So the core bit is a consensus log that is somewhat like Kafka, Red Panda, Pulsar, and so on. It's a Raft-based log. It's organized in a slightly different way, but that's not too important actually. The important bits is, beside the log, it contains two more things. It contains a component that actually computes over the log, and it contains a set of materialized indexes over the log that establish relationships between the events in the log. It's a push-based system, so when an event comes that is destined for a service, an event representing a service invocation, then Restate pushes that to the service. And one interesting sort of result of that is that the service doesn't necessarily have to be there by the time you want to call it. You can actually make the target of this event an API gateway with an AWS Lambda function or some other function as a service, and it just comes up in response to the event, goes away when the event is done. So it's kind of really nice match for sort of serverless auto-scaling infrastructures. So number one, it's a push-based system. Number two, the invoker component owns the lifecycle of everything. And number 3, Restate maintains a lot of contextual information about events, relationship of events, and so on in its indexes. And what does that actually mean? So it means that when Restate invokes a service with an event, it allows the service, while it's invoked with that event, to actually attach a lot of information to the ongoing invocation. Like it can attach long-lived state that actually goes across invocations. When you actually are invoked the next time, you get access to that contextual state again. And by attaching it to that invocation, Restate can internally actually make these updates atomic with the lifecycle of that invocation. You know, invocation succeeded, state is committed, invocation failed, state is not committed. It's a very useful primitive. It's not like you're not using Postgres anymore to store your state, but you actually have now a piece of state that is like always strongly consistent with your invocation, with the event processing. You never have to think about, okay, how do I get the acknowledgement and the state update atomic? You have a piece of state that's always atomic, and that's really, really, really powerful. You can use this for deterministic idempotency tokens, for like write-ahead information, it's actually insanely useful for lots of things. And it's a building block for a lot of like library extensions that we have. And the final thing is, in the scope of the invocation, the function can actually stream back partial progress information, and which gets atomically committed internally with the effect. And what that means is the following. Let's assume we have a piece of logic here that runs, and it interacts with a bunch of other services. You implement this in Restate just as you would implement an RPC handler. It gets invoked through Restate by an event that is in the log. It's the gray one over there, gets pushed into the service. And then as the service actually goes and does certain things, the effects of these steps actually stream back as events to the log in the background and get persisted, they get appended to the log. And then certain things happen. And I think it's especially interesting to look at that in the case of the yellow event, the RPC invocation of another service. What actually happens, this event streams back, gets appended to the log, and then Restate does two things. It indexes this into the context of the original gray event to say, okay, like the gray invocation has actually produced that event, and it also delivers that event actually to the target. And there's something interesting happens here, because we've kind of established two facts with one atomic commit. We've established the fact that our program has actually made that particular progress, and we've actually made the call to the other system. So it's kind of, we kind of have those two things now trivially in sync all the time. Like, where are we in our progress and what did actually happen? Those two things are together, and they're together with virtually zero coordination, because it's the same thing. It's the same log write that actually establishes the truth for this effect that this happened. It's just that then the invoker actually acts on this, puts it in the partial progress log here, and sends it over to the next service, shuffles it to another log partition on the next step. So if something crashes here, the recovery is actually trivial, right? Like Restate understands the connection is lost. It pushes the event to another service, it pushes the event again. Might be then a different service, might be the same service once it came back up. And it will attach this nested journal, the partial progress events that it already has internally. And that allows the function as it executes to actually see, okay, I'm doing something here, but I kind of have this in my log already, so it becomes a no-op when it actually does it again. In the case of the yellow invocation, what this actually means is the RPC promise that Restate creates basically gets recovered. And it gets recovered with the response. If the response came in the meantime, it gets recovered without the response and wired back to the response channel if it comes back before the response is actually there. So the code as it runs actually doesn't see that. It re-executes, it just goes there, and either the promise is already complete or they're not yet complete. It basically just like reworks on those, across those. That's it. So that's as much as I want to talk about theory here. Let's do the remainder of this in a very much like demo-driven way. We have a demo implemented. Demo gods be with us. We actually made it accessible. So you can actually go to that URL and order a pizza if you want. I mean, it's not actually delivering you a pizza, but we implemented an order processing system that in Restate that actually mimics order processing. You can go there or get some chicken wings, a pizza, some sushi, and so on. And it has all these things running in the background that kind of simulate that. This whole thing is actually running on it's just Restate and AWS Lambda. Like there's nothing else. Restate is kind of the gateway that accepts everything, and then Lambda functions actually have all the logic. So it's a completely serverless setup actually. And that's it. With that, I want to hand over to Giselle.
Yeah, so as Stefan mentioned, we will be showing an order processing app. So as you maybe already saw in your phone, you can select some products and then press a checkout button. So what then actually happens is that order that you place ends up on a Kafka cluster on a topic. And Restate subscribes to that topic, and for every event that ends up on the topic, it will trigger the order workflow. So the order workflow is the orange service you see there. It's a Restate service, which means that it has the SDK embedded, and it uses the SDK to do all the interaction with Restate for the workflow that it's executing. So the workflow will be doing a few different things. It will be communicating to some external services, such as, for example, it will charge the bank account of the customer via an external payment provider. It will talk to the restaurant in order to ask it to start the preparation of the order at the desired delivery time. And it will also talk to some other Restate services, such as the order status, which will keep track of the state machine of the order. So you can see the order processing workflow a bit as a state machine, where the order goes through being created, in preparation, in delivery, and eventually being delivered. And then the delivery part of the demo will be shown a bit later in more detail, and that's the part where you try to find the driver and then try to get the order delivered, and we will have the updates for that also streamed over Kafka. All right, let's have a look at our setup. So I already have like a part of the setup running. I have my Kafka cluster and a web UI running locally. And the next thing I will do is start Restate. So that goes very snappy because it's a single binary. I don't need to spin up anything else, no databases, or I will maybe make this a bit bigger for people in the back. I don't need to spin up anything else. It's all in a single binary. So basically now Restate is running and we have everything we need there. All right, the second thing we will spin up is our order processing workflow. So for that, I have here an order app implemented. I use the Restate SDK to create a server that will be serving two services, the order workflow and the order status service. So the order status service is the one which is keeping track of that order state machine. So let's run this. All right. Now the next step that we need to do is actually connect the different parts together. So in order to do that, I will run a simple curl command, which will register the services. So it's the delivery services as well as the order services. So when I run this curl command now, Restate knows where those services are running because we have a push-based model. So we need to tell Restate basically where the endpoints are, where it needs to push the events. And then Restate will actually also have a bit of a map of which services are running and where they are running. So when we, in our service, then want to call another Restate service, all we do actually is we just send that event to Restate, and Restate will make sure it ends up at the service and that it gets processed. So the second thing we need to do is create the subscription of Kafka, of Restate to Kafka. So this is basically letting Restate read from the orders topic. And for every event that then ends up, it will call an event handler. All right, so let's go now to the part in the code where we are actually going to process the events. So that's here. We have an event handler defined, and it gets called with a Restate context, which is basically the entry point to all interaction with Restate. It allows us to do all the features that the SDK offers. And we also get the event from Kafka delivered to us right here in the handler. So after parsing the event, we call the create workflow, and the create workflow then basically goes through the entire, all the steps to do the order. So I put some fail statements in here, which are basically going to throw random errors throughout the code to show how Restate will actually make sure that the code gets reliably executed exactly once, that things are not done multiple times, such as the payments. And for that, let's first create an order. So let's go to the web UI, which is running here. If we then for example, select a sushi box and some chicken wings, and we click on checkout. Then we see here the purchase overview, and we see that the status seems stuck. There's nothing happening here. It remains in status not even created. And the reason for that is that right now the code here is failing before it even gets to that point. So now let's slowly move through the code. Here we see the retries happening. We see that this number is increasing. So I'm running in debug mode with a TS no def setup, which basically will restart the service every time there's an error or every time I hit save. So as I am making changes in the code and I'm hitting save, the service will come back up. Restate will see that, will retry the invocation, and it will keep on doing that up to the point where the entire workflow is actually completed successfully. So let's have a look at some interesting features of what we can do with the SDK here. If I move this fail statement a bit down, for example, to here, then the first thing we do here is actually create this order in the order status service and tell it to switch it to the status created. So this is how you send actually a message to another restate service in a fire and forget way. So it sends it and it doesn't care about the response. It would be something you could implement with a message queue in some other architectures, but with Restate you get this out of the box, so no need for message queues. Restate will make sure that this gets actually, this set status call will get executed successfully. So when I hit the save button here, we'll see that it comes back up the service with the new code, and now the order is created. We also see that here in the UI, we see the created status. So that's communication between Restate services. Something else that is an interesting pattern is, for example, things which we really want to be executed only once, like handling a payment, for example. We don't want our customer to be charged multiple times. And for that we can use something called side effects. And side effects basically allow you to define a block of code, and the result of the execution of that block of code gets stored durably in the log of Restate. And so what you can do with that is basically, if you have a piece of code which is non-deterministic, such as, for example, the generation of a unique identifier, or a part of code which you don't want to get re-executed during every retry, such as interactions with external APIs or interaction with databases, then you would use a side effect to do that. So you wrap the code block in ctx.sideEffect, and this token will now, every time that there is a retry, be the same value. So if I, for example, let it fail right after I generate the token and I hit here the save button, and then we see during the retries, every time the ID is the same. So that ID is now stored in Restate, and for my invocation, I'll always get the same one. All right, let's move a bit further down the workflow. For example, here we have another interesting pattern. So imagine you want to order a pizza for 9 o'clock in the evening, and if a customer does so, you want it to be durably scheduled for that time. And no matter what happens, infrastructure failures, all kinds of stuff, you want it to really be executed at that time. Then Restate gives you some primitives to do durable actions in the future, so durable timers basically. And there are actually two things you can do. Either you can let the handler sleep for a certain amount of time, or you can ask it to do a delayed call to another service. So for the sleep, what that actually means is this handler will not keep on running. So if you would do that in, for example, AWS Lambda, your Lambda function will be able to suspend during the sleep. Restate actually lets it gracefully shut down for the duration of the sleep. And by the time the sleep is finished, Restate will re-invoke the Lambda invocation, and the Lambda invocation will just continue where it left off, which will be exactly here at this sleep point. So none of that gets re-executed. And just for the sake of completion, for example, sending a delayed message to another service would be something like this. If you want to send a delayed message to the order status service, you just supply it the delay you want and then ask it to, for example, set the status at that specific time. So those are really interesting primitives that are actually very difficult to implement without Restate, but with Restate they become one single line of code and you don't need to worry about anything. Like, as you see, the code is actually super simple. Like, you don't need to write retry loops, you don't need to worry about all the ways your code can go wrong at every point throughout the execution. Restate takes care of all of that. All you need to do is just use the SDK to interact with Restate at the important parts throughout the code. But so most of the things I now showed were actually communication, for example, between Restate services. You can also communicate to external services that are not Restate services, not using the SDK. For example, imagine that for our use case, we have a restaurant point of sale system running somewhere else. And when we are done with waiting for the preparation, we want to tell the restaurant to really start doing it. So this is basically, we're calling a restaurant client to ask it to start the preparation. And one way we can then ask this restaurant to communicate back to us that it's done with the preparation is through something we call awakeables or persistent promises. And that allows you to actually create two things, a promise and a callback URL or an ID. And what will happen then is you send the callback URL or the ID to the restaurant together with the request to do the preparation. And when the restaurant is done with that, which can be in 1 hour, in 2 hours, it doesn't matter for Restate or for our handler, after that, it will deliver this ID back, or we'll use that callback URL to invoke the workflow again to continue to the next step. So during the time that here we are waiting on this promise, basically, which is the promise which will be resolved by the time the restaurant lets us know that it's done, during the time that it's waiting on that, this handler will also be gone. Like, Restate will re-invoke it once it sees, okay, this workflow can now continue what it was doing. All right, then let's remove this failure here to let our code progress a bit. Okay, we see that it got through the status as scheduled and in preparation. We also see that happening here in the UI. The final part of the workflow here is creating the delivery. So that's a bit a similar pattern as what we did with the restaurant. We will ask the delivery service to start the delivery and just let us know when it's done with that. All right, our order got successfully delivered. There's one more thing I want to show, and that's basically how we implemented this order status service, because it's super simple and actually very consistent and nice to use. And for that, we used basically the key value store of Restate. So what we did is we use ctx.get and ctx.set to store values in Restate, and those get committed and kept up to date together with the code. So let's, for example, query this key value state store for the cloud deployment that we have. So if some of you would right now be placing a order on the URL we gave a bit earlier, then we should see this coming up when we execute this query. Okay, I will do one myself just to show that it shows up to those who aren't trying it out. Okay, so Marnie placed an order, and this is all executed in Lambda, and we see here Marnie coming up in our query. So we see how it goes through the several stages. Every time you see this switching from one to the other, that's basically that order workflow calling the order status that it's done with another step of the workflow. And all of that runs on Lambda in quite an efficient way with the suspensions and everything Restate allows you to do for that. That was it for the order workflow. Now I will hand it back over to Stefan to show you a bit about the delivery part.
Can you take this? Okay, cool. The AV setup worked. That's perfect. That's a good start. Yes. So let's look at the second part of the this demo implementation. There's maybe one or two things quickly that I want to point out that's maybe really worth stressing here. So number one. All those things that we did in the order workflow, right? Like, capturing as a token and a side effect and so on, making these calls. Those are actually, they look simple, but if you want to get them really, really reliable, they're actually really hard. It's not the same as actually going and saying, oh yeah, I do a random ID and I'm writing that in a database. Because that implementation is actually resilient to like partial network partitions and everything, because you have the ground truth log that drives everything, that understands, one invocation supersedes another invocation, fences this off like with an epoch-based mechanism, and understands that no two results can ever make it there. It's always one that makes it there, and that one will be the authoritative thing that is used as the basis for everything that comes after that. So like, if you really try to actually get that yourself, you end up like working with the database and semantic locking and so on. It's like, it's not trivial to do that, even though it looks. And it's probably something that most people don't think about when they implement application. And then like once every few weeks, something gets lost, because you just have a situation where you're still connected to your message queue, but not to the database or the other way around, and you just have some things that actually override each other, even though you were not expecting that process to even be active anymore. And this is not happening here. Like, this is basically getting out of the way. The second thing I wanted to quickly point out is that what Giselle showed you, the queries over the internal state works it's basically a SQL engine over these indexes that Restate has. So the indexes kind of index the relationship between events, and there's like a lightweight SQL interpreter based on Arrow Data Fusion that you can actually use to query those. And that's where we draw all the information from. Okay, let's actually get to the second part. The second part is that the interaction of the drivers and the driver pool and so on. This is in contrast to what Giselle showed before, not a single long-running function, not a single workflow driven by an event, for example, from Kafka, but it's like a set of small services interacting with each other. Like, we have the driver service, which follows like the digital twin pattern for the driver, which understands the status of the driver, interacts with the driver pool to make itself available to accept an order. What's really nice is, again, the ability to basically have state and communication and so on, everything tightly together. For example, the driver pool implementation here, the function to make a driver available is basically just that. You have the two branches where you say, do I have waiting requests? If yes, I immediately give one of the waiting requests to the driver. Otherwise, I remember the driver is waiting. And if an order comes, it's the other way around. And you don't have to worry about assigning a request, but then a response to the RPC fails, or the other way around, and you're losing a driver or a request on the way. Like, nothing of that ever happens. It's like reliable end-to-end, exactly once event processing, basically, but written in an RPC-based manner. And that's the other important thing. When we do things like this that look like RPCs, they're not actually RPCs. They don't even really function like RPCs. It's not an RPC abstraction bolted onto an event stream. What actually happens is, we call this RPC for simplicity. What actually happens is this creates a promise for an event to be completed. And it's basically awaiting on a persistent promise with all the things that come with that, right? Like the ability to suspend if you're waiting for an answer and the answer takes a while. For example, this call can actually take a while. You're asking to assign order to a driver. If that takes longer than you expect, the thing will go away. It's like you have a state machine, and you don't need to keep the state machine running. You have the state of the state machine persisted, and it comes back up when the relevant next event is there. So you really have actually asynchronous distributed event-driven state machines that you're working with without actually specifying them like that. The way that, just to help you understand the code a little bit, it really is actually implementing RPC services, even though it doesn't look like that here. This is kind of a more functional TypeScript API. The way you can think about it, though, is that all these functions are methods of a service, and the way you group them together in a router is like, this is now a service. There's also gRPC API, but that's just like a lot more verbose and fits less code on the screen, so that's why I've actually used this like more fine-grained functional API here. The other thing that's actually kind of fun here is this service is partially driven by RPC and partially driven by events from Kafka. And you do this without embedding a Kafka consumer in there. In fact, actually, you have an endpoint where you can decide, oh, I want this invoked by Kafka, by RPC. RPC. It's really just like, do I wire up a Kafka subscription or not? It's the same thing, like RPC, event-driven, it's all the same thing in the end. Okay, so a final thing that I want to show is the following. Let's actually get back to triggering an order here. Let's check this order out, and at some point in time when we have a driver and everything, actually place the breakpoint here. So we should eventually see this order being, not making progress, but getting suspended, like the whole communication should get, or the execution should suspend. Here we go. So we basically just interrupted this. By the way, this is the beauty of developing, and like in this model, we just have a service that gets pushed to and so on. You just really started from your IDE, register this with Restate where it runs, and you have this like incremental recompile development workflow. It's really beautiful. I can hardly recommend it if you've worked, especially coming from the Flink side before. So what we have now is we have actually this thing blocking. Let's assume this is a situation that we're observing in production, like that something's just blocking. And it's not making progress. So what can we do now to figure out why this makes progress? And then Giselle already showed you the shell, the SQL shell that allows you to query like the indexes for the state. You can actually also, because the indexes also index the relationship between events when it comes to invocations, you can also use this to actually query the relationship between invocations. So that's what we actually have in the top window here. Right? We see actually driver B, is invoked by, okay, simulated driver is actually the drivers that actually move around. They're actually reset services as well, because that was the easiest way to implement them. And we can actually see that this one is blocked on another one. So we can actually even in a more specific way like ask, okay, like, hey, what is the relationship between those? Like, who's blocked? Like, who's blocking a service that is getting suspended? So this is the query we would be running. It's a self-join between the sysstatus table to tell us who's blocking whom. And would actually, if we execute that, find that out. You know, this simulated driver B is actually blocked by driver B in the method notify delivery pickup, which, oh wow, that's the one actually that I intercepted here. Very good. So let's actually resume this. The whole order workflow starts progressing, and if we, now we actually shouldn't see this anymore. Good. So we actually have a way to kind of query the distributed invocation relationship between services, because this is actually materialized asynchronously in an index through this event-driven system. Okay, I hope that this is an interesting, just short summary of what you can do actually with a system like this. Like have an event-driven system between your services, but don't make it just deliver the events. Make it actually aware of what the events do. Make it actually able to index the relationship between events. Make it actually interpret events as state and as partial progress and relationship and so on. You can build very impressive things on top of that. Nowhere, I just want to stress this, nowhere in this code you see like retries, catching like lost connections, like anything. And that doesn't mean that this doesn't work, right? Like Giselle showed this like with throwing the exceptions. It's going to be very hard to destroy this. Like it's going to be very hard for you to implement something that is that resilient without Restate, just because you would have to ground so much information with each other, like invoke this system, that system. You basically get with this a source of truth, a log, that kind of represents, that allows you to really fall back to a consistent point in every failure. You don't have the problem that, an event and an acknowledgement and this database update and that. You kind of have to figure out the distributed sort of status and consistency model between all this. You get a very simple one out of the box. And yes, you would have to extend that if you, for example, interact with other systems, but there's actually really cool ways to do that. That's probably going to be another talk where you can use this to make this like the coordinator for transactions against other databases and really tie everything together that way. The final thing I want to show, and this is really, okay, this is very, very, okay. I basically hacked this together on the flight and yesterday evening. It's actually stream processing with Restate. So here's a thread from Jake Krebs from about 6 years ago. Stream processing as a protocol. It's a very, very good thread, I think. Actually back then got me really thinking. It's actually the case for Kafka streams. I think it's the 1.0 released Kafka 1.0 thread, but it has the section on stream processing as a protocol. A lot of good stuff in there. Like you can actually revisit this thread today, and you will actually agree with a lot of what he wrote there. The one thing I would say though is yes, probably stream processing can be thought of as a protocol, but maybe it should be a slightly different protocol, because if you look at how many implementations of Kafka streams are really mature, it's probably the one in Java, because really making this protocol work is far from trivial. Just the complexity of managing RocksDB timers, back pressure on, it's really, really hard. But what if the protocol was actually just that? Stream processing is event and associated state, go into transformation, and it spits out downstream events and a delta to the state. What if the stream processing protocol was just that? And funny enough, the Restate protocol is kind of close to that. It's actually slightly more general than that because it captures partial progress and sort of attached contextual state and so on. But you can actually use it just like that. It's kind of a subset of the Restate protocol. So that's what I tried to hack together here. So there's a very simple stream processing library. I'm not sure if you can read this. What this tries to do here is it takes these location pings that the drivers send, then it is a mapper over them where it rounds them to a 100 by 100 grid, and then keys by that grid and just counts like how many drivers are active in each city grid at any point in time in like 5-second windows. It's an extremely simple thing, but it's actually stateful, and let's actually first see if it works before I say anything else. So let me actually just send off a few drivers. So maybe this one, actually let me prepare them so I send them off at a similar time. Okay, so this one, that one here, and this one here, and this one here. And what we should be seeing here is, that's basically our, I'm not sure if you see this. It's again a SQL query over Restate's internal state store, because that's where we basically materialize this. So by the way, if you're coming from Flink, it's basically queryable state in SQL over your internal state. And that's it. And what's your guess? Like how many lines of code is that stream processing library? It's actually 325, and that's only one to get function chaining in there. So you actually don't get a stage for each invocation, but like only between shuffles and everything across shuffles gets fused together. So that is it. I mean, for all fairness, I think what we have to say that this is not a perfect stream processing library. It's actually a shit stream processing library, if I'm quite honest about it. So it has very few transformations in there. It's actually going to have abysmal throughput because it's just like TypeScript JSON serialization for everything. It actually goes through very fine-grained consensus, which is not great for throughput either. It's actually great for latency, not great for throughput. It doesn't actually have any back pressure, and it doesn't have any event time. So fair enough, maybe that's what you expect for a 320-line stream processing library. But at the same time, it's actually exactly once. It's actually very low latency, end-to-end exactly once low latency, like in the 100 milliseconds end-to-end exactly once latency. It actually supports large state because the state is not materialized in the stream processing library. It's actually in the Restate broker. It actually allows you to do zero downtime upgrades. Maybe we can actually try this out if we have 50 seconds left. Okay, maybe after that. So you can actually just edit it and save, and the process will restart, and it will accept calls to the new code version. It actually scales the compute independent of the storage. It has a dynamic parallelism. Nowhere there do you define parallelism. Restate internally manages parallelism by key in kind of a recursively splitting partition model, and the library doesn't actually think about parallelism in any way. It just thinks about keys. It actually allows you to have to really query the state, and it allows you to actually see tracing, like interactions across everything. So that's not nothing, right? I mean, there's lots of limitations, but there's also lots of things we get out of the box. And yeah, with that, we'd like to conclude this. And so what I hope you can take away from this is here's an interesting new take on event-driven applications, like building them without thinking too much about event-driven applications, and a system that implements this very specific protocol that allows you to process the events, to interact with them, or to back these APIs with which you write these applications has a very specific model in how it thinks about compute, state, partial progress. And this allows you to actually build very sophisticated applications in a pretty simple manner, be that workflows, be that distributed microservices, or even something like stream processing. That's it. Thank you. I think we're already over time.